Hey guys, this is Larry here, and today I'll be presenting the Module 3 project for the ECEN 2350 Digital Logic class here at CU Boulder. And today's project, we got a reaction timer. Okay. Today we have our project goals of creating a reaction timer using a Verilog code and our DE0 board. Right now I have the basic. I have the reaction timer from the book that's coded and shown here. Basically, we have a reset. Okay, we have a start time and a stop time, and as noted here in the PowerPoint, we press the start button. We have a LSFR, LFSR, generate a random number that determines a random wait time before the timer actually starts counting up on the 7 segment. Okay. And we need to generate this 100 Hz signal that'll be used as our timer for how long it takes for us to press the stop button after our start LED turns on. Okay. So here are some goals. We're going to take the default 50 MHz signal and drop it down to 100 Hz. We're going to create a binary to BCD converter. We're going to get the BCD and have that display on the 7 segment displays. We'll create a state diagram for our reaction timer. Use of submodules and Verilog code to make the reaction timer in Verilog using a recorders program. And then record the delay times of a reaction timer and demonstrate the reaction tester. Just for those who don't want to watch the whole video, because I know I can make long ones, I was not able to do the last two because I was not able to implement the LFSR into my reaction timer, although I did get the LFSR to work correctly. Okay, so before I continue with the different components that make up the reaction timer, the generator, the generator, the converter, the display, I just want to note that it is important that you can make these modules using gate level implementation, but since we have the power of Verilog code, there's also a Verilog implementation that will be used for this case, and I will talk about both implementations for each major component of this reaction timer. So starting with our 100 Hz signal generator, it's the thing that drives up the 7 segment displays and shows how much time has passed after pressing the start button and before pressing the stop button. Okay, and 100 Hz is 1/100th of a second basically for each one. It's important to note that our Altera DE0 board has a 50 MHz signal already built into it. And doing gate implementation, we can use tethered T-flops, so like feeding the output of one T-flop into the input of the next one. So like Q of one T-flop into T of the next one. That would basically drop the signal frequency down, and then using the Qs of each of the T flip-flops in between to then check for 249,999 in decimal, and once so we can use OR gates and AND gates to check for which of the Qs that are needed for that decimal number to go high, and once that condition is met, past that that will go high, pass that through one more flip-flop, and then pass that high signal also to all the synchronous reset of the T flip-flops. So it is important to note that there is an example of this in the textbook. Let's see here. Do excuse me, I may pause every now and then. I didn't want to just flip through the book, wasting time. But for example, on page 274 of our Fundamentals of Digital Logic with Verilog Design, we do have an example of this tethered T-flop design with the synchronous clear and enable. Okay, that was just an example. So instead of the 4 that are pictured in the book, there'll be 18, and then there'll be an extra AND gates and OR gates to check for some of the Q outputs for when they go high, to check for that decimal number. Okay, so very Messy? Yes, it can be done in real life with actual like CMOS chips, and yes, this can be done in Verilog this way, but it's very messy, very just very long, and just a lot of debugging because there's so many pieces of this code that you would have to check, and so many points of errors. Okay, so instead of doing this gate implementation, we can just use Verilog implementation to create a variable that would increment each time the default signal went high, and then check each time what value that variable is, and once it reaches 499,999, the counter resets to 0, and our output register, which will be our 100 Hz signal, gets shifted up, and then gets shifted back down. So basically, we have two variables that are created, a counter variable and an output variable. The output variable will go up when the counter variable reaches 499,999, and then drop back down, and then the output variable drop back down, and then it repeats, which is basically the same thing as going high 100 times per second, given that the signal that we're feeding in is a 50 megahertz signal. So, leaving the presentation and going into our Verilog code itself, you can see here that this is my module for the 100 Hz generator. Okay, I use the Verilog implementation here, where we have our counter variable, we have our 100 Hz signal variable, and we have our input 50 megahertz clock signal and our reset clock signal. Okay, and we basically do a procedural statements where it'll check these every time we get a positive signal from the default 50 megahertz or a positive edge from the reset. Okay, and if it resets, set both the counter and the output to 0, or else check for that 499 with the incrementation, and then if it reaches bit shift 1, and then reset the register, and then it does it over and over again, generating a 100 Hz signal. Okay. In addition, the BCD count and the 7-segment display, it's important to note that we've done this in previous projects where a Carnot map and a function could have been made for both the BCD count and the 7-segment display, but instead we chose to do Verilog just for the sake of simplicity. So the BCD count takes in our clock signal, and it basically counts up from 0 to 99 and then resets itself, having two variables, one's for the tens place and one's for the ones place, and each of those variables are 4 bits long. And basically it increments it every time we get a positive clock or a clear. So if you get the clear, it resets both to 0, and if we get a positive clock, we increment unless the ones place has reached 9, then the ones place resets, and then the tens place increments one time. Or else, if both the ones place and the tens place were 9, then they'll both reset to 0, and that's basically your binary to BCD converter. Okay, and we've done the 7-segment decoder using a Carnot map and functions in the first project with a gate level implementation, but for the third project we're trying a more sophisticated approach with cases, in which it's always going to check as long as the BCD has a value, which is all the time. We're going to have these different test cases from 0 to 9, and which segments of the 7-segment display should go high. Do note that the LEDs for the 7-segment display on the DE0 board are active low, so the zeros actually mean a lit up segment. Okay, and we'll always have one of these test cases, but we do need a default test case, which is basically a random number of bits. And this is like a little debugging thing. Like, we'll never get this, but if we do, something went very, very wrong because none of the other test cases were met, meaning just a random number of segments turned on. That's what the X means, just random. And that's it for our binary to BCD converter and our BCD to 7-segment converter. So with that, we have the major components of the basic reaction timer, per se. Okay, and I just want to let you know that the other component that we needed was the LFSR. Okay, and here I have my LFSR, a very simplified LFSR, but it works nonetheless. It's important to note that the LFSR, as shown from this example here, that it's just a bunch of D flip-flops in which the last 2 bits are XORed and fed into the first flip-flop, where each of these flip-flops is basically bit shifting it's basically a bit shifter to the right, and the last 2 or the first 2 bits get XORed, and then whatever the result of that XOR is gets fed and it gets pushed through. So it's not really random generation. Like if we take all those Q outputs in blue, it would generate a number of length n. And it's pseudo-random because the next number does depend on the previous state of the flip-flops. And here in my Verilog code, I do have that here, which is basically, let's have a an 8-bit number where we XOR the first 2 bits and bit shift it back into the last bit. And that's basically what's happening here. But instead of defining the individual flip-flops and using for loops to make some complicated mess of a code, I'm using just the simple shortcuts that Verilog offers for coders to make the same circuit, but much less lines, much cleaner, much easier to read. My problem with this project was that I was not able to implement it into the actual reaction timer, so I don't have a random time. But I do have a reaction timer basic, and I'll explain how that works. Hey guys, sorry about that. The program I'm using has a 15-minute time limit, and I went over it, but I assure you I won't be as long this time. I just need to explain the basic timer, the overall timer, and then conclude it, and we'll be all good to go. So with the basic timer here, we have our clock signals, our reset, a start button, and a stop button. We have our LED, our LED that turns on when the timer actually starts. Okay, and we just have our variable LED that's used. Okay, so here we talk about the assignment of the blocks, and then we'll talk about the procedural statements that follow. So here we have our 100 Hz generator, which takes in the 50 megahertz, has a reset, and outputs 100 Hz. We have our BCD count, which is basically, let's count the cycles of the 100 Hz signal, and that outputs, that takes in the LED variable, has a reset, and it takes in the 100 Hz signal, and it outputs 2 BCD numbers, a ones and tens place, ones place, tens place, and we have our 7-segment converter that takes those 2 numbers and outputs them on 2 different 7-segment displays on the board. So the actual magic here, this is where the actual magic happens, because when we push the stop button, or when we press the reset switch, the LED variable goes to 0. But when we press the start button, the LED variable goes to 1. So when this LED variable goes to 1, the LED N, or the opposite of it, is actually the, excuse me, that gets a tilde there, whoops. But that turns on the LED that says, hey, you should press the stop button as soon as possible. And since this LED variable goes to 1, this is the enable for the counter, meaning that once that goes to 1, the whole counter starts counting up. So you'll see, just like on this board, let me reset it quickly. Oh look, it's counting up. I should stop it. Okay. Oh, sorry, I pressed a button on my keyboard. But it counts up, Here, let's reset that again. It counts up until the stop button is pressed, which is basically this part of the code right here. Not push N, LED goes to 0. Okay. But the reason why the display stays the same is because the reset for the display, the reset for the Hertz signal, and the BCD count is actually the switch, not the button. So yeah, you could start it, and you could stop it, you could start it, and you could stop it without resetting it, but as soon as you hit the switch, the 100 Hertz signal and the binary to BCD counter resets to 0. Okay, so that's your basic timer right there. The only difference between this and the actual thing the project was asking for was changing the condition here. So we have our basic condition of 0, but when we wanted to do a delay when we hit the start button based on what the LFSR returned. So that's where this Q final comes out. And I just didn't know how to do that. I tried doing if statements, I tried doing while loops, but in the end I do believe the answer was using a counter and having this a counter variable that would count up to whatever the Q final number was, and once they were equal to, set the LED to 1, which would essentially mean press the start button, take the value of the LFSR at that point in time the button was pressed, and have the counter variable increment now until it matches the value of the LFSR, in which after that is met, turn on the LED and start the timer for you to press the stop button. That is how the actual timer was supposed to work, but I was not able to get the actual delay to work on my end. Okay, one of the last things I need to talk about would be the state diagram. Okay, and here, let me go back into full screen mode right here. Oh, I gotta switch the view. Don't know why it does that automatically, but oh, ooh, too spooky. But here in this bottom right hand corner, you can see a hand drawing I made of the state diagram. We have 4 states here, and we have the arrows going in between the states. So state 1, our S1, is all the segments are 0, the LED is off, and the start button was not pressed. State 2 is the 7 segments are still 0, the LED is still off, but you press the start button. State 3 would be the 7 segments start counting up, the LED is turned on, but the stop button has not been pressed yet. And state 4 would have been the 7 segments are stuck on some position, the LED is turned off, and the stop button was pressed. Okay, and then we have our transitions here. So to go from 7 segment all 0, LED off, button not pressed, to all 0, LED off and pressed, I mean, the transition would be to press the start button. And then to move from state 2 to state 3 would be to, now that the start button's been pressed, the LFSR has a random variable, and the counter variable is counting up, and it just has to wait for it to match. So that's the random pause time determined by the LFSR. And to go from, so now we're in this state. State 3 is this state, basically. Oh, it's counting up. Oh, the LED's on. I should press. Oh, sorry, that's a reset. Oh, I should press the stop button. And that's how you get from state 3 to state 4, would be to press the stop button. Okay. And then we do note that we can also go back from state 4 to state 3, which is from this state to this state. And that's basically by pressing the start button again, letting the random time pass, and then there you go, state 3 again. But it's important to note that not all the arrows, so in a typical state diagram you would have arrows going from all the states to each other and back, but some of the states are just not possible here. For example, I can't go from all 0, LED off, start button not pressed, to automatically at some number, LED off and stop button pressed. It's just not possible. And the same thing as going from state 1 to state 3, because you need to press the start button in order to go from state 1 to state 3, but that means going through state 2. Okay, and lastly, we have this X state here, which is basically our reset state. You know, it brings it back to state 1, state 1, state 1 from all the other states, except it's also possible. I mean, technically, this is the same as going to that, because the segments are 0, the LED is off. It's just the matter of change of whether the start button was pressed or not previously. But when you hit the reset switch, so if I'm here, I'm in state 3 right now. I hit the reset switch. Oh, look, I'm in state 1. Okay, I start it up. I stop it. Oh, look, I'm in state 4. Hit the reset switch. Oh, back to state 1. Okay. State 2, I can't show because it's one of those weird states that it happens in between. But yes, you can go from state 2 to state 1 by pressing the reset switch. And that's really all I have for the project. I showed you our goals. We have our 100 Hertz generator. We have our binary to BCD converter. We have our BCD to 7 segment converter. We have our basic timer reaction. We have our way of generating a random pause time using the LFSR and a secondary counter. The only problem was I was not able to implement the delay itself into the code for the actual counter. So, according to the guidelines of the project, I did 75% of what was asked for. And embellishment for the reaction timer, to be fair, I do play League of Legends, so I did get some of the pizzazz points for this project. But if you have any questions, please leave a comment or message me directly. Thank you very much for sitting in, and do have a nice